So, welcome and good morning. So today we are going to discuss about fields and differential operators. So the topic today is fields and differential operator. Shear operator. So the field is basically used in physics and mathematics. The field of a physical quantity means that it is a function of position. Yeah. So suppose the light bulb, the bulb creates in this room, the bulb creates a field of luminous intensity, because you have at every point on the space you have certain luminous intensity of the light. So suppose you have a bulb here, light bulb, and you will find that at every point of the space you will get some value of the luminous intensity of the light. It means you can say that this bulb creates a field of light intensity around it. Similarly, if you suppose there is a hot body, you will experience temperature at every point in the space. You will get certain temperature here. Everywhere you will get certain temperature. So you can say that this hot body has created a field of temperature around it, because the field is a function of positioning. For any field of any physical quantity means at every point in the space it has certain value. Then we can say that it creates a field. So now in next example, suppose you have a charge body here, positive charge Q. Now if you bring a unit positive charge here, you will experience a force on this unit positive charge, which is called electric field. So for every point in the space around the charge, you will get certain electric field. You will get, because this is the force experienced by the charge. And since force is an vector quantity, it means this type of field is a kind of vector field. And this was the temperature field, and temperature is scalar quantity. This hot body has also created a field around it, but this is a field of temperature. But temperature is a scalar quantity. So this is a scalar field, example of a scalar field. Bulb has created a field of luminous intensity around it, and this is also a scalar quantity. So it's a luminous intensity is a scalar quantity. Luminous field of this luminous intensity is also scalar. Field of temperature is scalar. But what about this electric field? This electric field is the force, and force is a vector quantity. It means this is a vector field. The force electric field is outside the charge, radially outward. So it is the electric field. So similarly, you can say that electric potential or gravitational potential is the energy. So that the energy, the field of the potential energy, or the field of electric potential, because the electric charge produces a field of potential also around it, and since potential is a scalar quantity because it's an energy, so it's an energy field, or we can say it's a scalar field. So we can say that fields, we can divide field into two parts. called scalar field. This, we have a temperature field, light intensity field, potential field, all types of potential gravitation, electrical potential, because all these are energy. All these are examples of scalar fields. Now, so we have a vector field. Examples of vector field is electric field, gravitational field, and so on. So in this we have found that fields are of two types, scalar and vector. Now the next topic is differential operator. What is our differential operator? So differential, this symbol, differentiation with respect to all three axes. Suppose the coordinate axis, rectangular coordinate axis. So it is del x, del y plus del y, del z k. This is represented by a symbol like this, and this is called differential operator or simply del operator. So del operator is nothing but its differentiation along all the three axes. So this differential operator, when acts on the fields, it creates a new field. So when this differential operator acts on, suppose, a vector field, let the vector field is considered a vector field denoted by A. If this operator operates on a vector field, this gives you a new field which is a scalar field. And this is called divergence. Divergence of the field A. This means divergence of field A. And this results in a new field which is a scalar field. Okay? Now when this operates on a scalar field, when this del operator operates on a scalar field, suppose the scalar field denoted by phi, this is a scalar field. This is called the gradient of phi, and this results in a vector field. Oh, yes, vector field. This is called gradient of phi, field phi. When we operate on a vector field, we get a scalar field. When we operate on a scalar field, we get a vector field. Now, once again, when this operator operates like this, here it's dot, here it's cross, on the same vector field, and this results in a vector field. And this is called curl of A. Curl of A is a vector field. We will discuss independently in these divergence, gradient and curl, what they gives. This is a vector field, and this field is perpendicular to the outflow. So we will discuss later on. We'll finish then. So first of all, what about this divergence of A? The divergence of A actually means, this is a scalar field. This actually means, we will discuss this, actually means the flux of A. Flux of A through the surface, the whole surface area. Okay. So, and before discussing this, we will discuss what is flux, then we will do divergence. What is a flux? Flux is always associated to a vector fields only. The flux of a vector field means the flow of the field per unit area per second. Suppose consider raindrops. These are, suppose the mass of each raindrop is same mass and the velocity is also same, v. So the momentum of each raindrop is P is equal to mv. Okay. Now consider a plate. Now this plate, the area of the plate, the area is a vector quantity, you know, the area is a vector quantity, and area of this blackboard means this is the area of the blackboard. If you put your right palm, rotate fingers, and that gives you the direction of area. So if you have a plate here, then the area of this plate will be, so this will be the area of the plate. Direction of area. If the area is a vector quantity, it has a certain direction, and the direction is perpendicular to the surface. Now, this momentum P if we want to find the total momentum which is passing through this area, that is momentum flux. This will give you, will be P times A, momentum into area, because as you increase the area, the flux will increase, decrease the area, flux will decrease. Now if you put the plate like this, the area is in this direction and the momentum is, so it is no flux of momentum through this area. We can say that this momentum vector and area vector makes a kind of dot product. So we say that P dot A, because when P A cos of the angle between them, cos theta, when theta is 0, in this case, because the direction of momentum is also along this and area also along this. So these are parallel. The angle between them is 0. Cos 0 is 1. So the total flux is here, total flux P dot A, which is equal to PA, momentum into area. Now if you take theta as 90 degree in this case, and cos 90 is 0, so this is the total flux is. So we can say that the flux of the momentum on this area is P dot A. Now, so if the momentum here we have assumed the mass of each drop same and velocity of same, but in general this may not be the same. If this is not the case, when momentum of all raindrops is not the same, then what we do, we divide the whole area. If suppose this is P1, this is P2, this is P3 and so on. So what we do is we divide the whole plate area into small surface areas, very small. We divide the whole area into small areas and assumes this area is so small that momentum in this region remains constant. Then the momentum in each region is constant. So that if you want to find the total flux, what you do, you find the flux in this small area, plus this area, and the summation of all the fluxes will give you the flux of the raindrops or the flux of the field through this area, the whole area. So the flux, total flux will be total momentum flux to the whole area will be like this. P1, you have divided the whole area into small areas, say dA. This one is area dA, and dA, the dA. So it will be in the first area, this is the momentum is P1, so it is dA. Plus in another area, it is the momentum P2, dA, plus P3, dA, and so on. The whole flux, total sum of the fluxes will give you the total momentum flux. But here we have assumed this dA must be very small, so small that the momentum in that small region does not change. So that can be, this is written like a symbol, limit, mathematical way of writing this. Suppose dA instead of delta A. It's better to take that as a delta A. So limit delta A tends to 0, and we write it like this: Pi delta A. I is say 1 to n number of areas, n may be very large. So this way of writing this whole process can be written by one symbol, P dot. So this is the flux of the momentum. So flux of any field, say I have written, okay, so I am removing this, erasing all these things. So when we have understood what is flux, so the divergence of A means, so divergence of A, or say divergence of A, which is a scalar quantity here, scalar field, and this is actually means flux of A to A per unit volume. You consider a small volume and the flux of that field A to that per unit volume, this is called the divergence of A. Or this can be written as flux of A means A dot ds, where ds is the small surface area integrated over the, so this is the flux, and divided by the volume. So you can write limit delta V tends to 0, so divided by the volume, where the volume is very small. So this is the actual meaning of the divergence. Okay. Now, physical meaning of the divergence. Physical meaning of the divergence. Consider a cube of sides small cube, but I am drawing big, larger cube, but actually taking this sides is small, so it's a cube. So the sides corners are A, B, C, D, E, F, G, H. These are the corners A, B, C, D, F, G, H of the cube. Of sides, so this, if we suppose this as our x-axis and this as our y-axis and this as z-axis. So this side is, say, this length is dx, this is dy and dz. So a cube of volume, say, dx, dy and dz. Okay. And suppose a fluid, an incompressible fluid of, say, density rho is passing with velocity v. So the velocity along x-axis is bx, and that along component of velocity along y-axis vy, and component of velocity along z-axis bz. So the velocity of the fluid which is passing along x-axis, say vx. So if we multiply the density by the velocity vx, so this is mass per unit volume, okay, and this is length per unit time. Velocity is distance traveled by time taken. So the dimension will be this. Suppose this is mass by volume and this is length by time. The volume has length at an area, so length cancel out. So it is mass passing per unit area per second times. So it is the mass of the fluid passing through per unit area per second through along x-axis. So we can say that mass of the fluid passing per unit area per second along the x-axis. This is between by rho dx. So this is the mass of the fluid passing per unit area per second through this. So the mass of the passing through the surface, this surface area, the flux of the fluid through the surface area from this surface area ADHE, ADHE and this area is, this is dz and this is dy. So this area is dy dz. It is dy. So the flux of the fluid through the surface area will be equal to, which is the flux, which is the mass. This is the mass flowing per second per unit area. Then the flux through this area will be rho times Vx dy. Mass of the fluid through the surface area per second. So this much mass is passing through this surface area, and if this is passing, then what is emerging out of this surface? If this is passing, this is coming out. So you will find what is the mass which is coming out of this surface area, B, C, G, F. So mass of the fluid through the same surface area dz dy through B, C, G, F, through B, C, G, F will be equal to, so this mass is entering, and during this distance the velocity of the fluid may have changed. In this distance, passing through this previous distance, the velocity, if this is entering with the velocity Vx here, and maybe the velocity is changing, suppose the velocity is changing, that the rate of change of velocity is dvx by dx, and this rate of change this is rate of change, and in how much length? In this length. So what is the change? So this is the change in velocity. So if you write here, the mass that enters here is this much, plus the change in the velocity. So that change, this is the velocity which enters, and the velocity which comes out, the velocity may have changed. So this will be dvx by dx into dx, and this area again dy. So if this is the amount which is entering, and this is the amount which is coming out of the surface, this is entering from along the x-axis, and this is coming out of the x-axis. What is the flux which is coming out of this cube? The difference will, so if you divide, subtract, you will get the mass of the fluid which is coming out of the cube along x-axis. So the mass of the fluid coming out of the cube along x-axis per second. Will be the difference between these two. This was equation 1 and this is equation 2. So the difference will be subtraction. Subtract this by this. If you subtract this, these two cancels out and you are left with this. So this is rho dvx by dx, dx, dy, dy. This remains. So this is the amount which is emerging, coming out of the volume along the x-axis. So if here we have considered only along x-axis, similarly we can take along y-axis and z-axis also. Similarly for other axis, similarly for y-axis, this will be rho. It's the velocity along the y-axis dv by dy, dx, dy. And for z-axis, this will be rho times dvz by dx, dy. So if you add this whole, is the flux through the holes, flux out of the volume will be the sum of along x-axis, y-axis and z-axis. So the flux of the fluid out of this cubical volume will be so this is the flux of the fluid through the volume, through the cubical volumes, through the dx, dy, dz, this is the volume, is equal to rho times delta v by delta x plus rho times delta v by y delta y plus rho times delta vz by dz. Dx, dy, dz you can take out. So this will be dx, dy, dz. So this is the flux and this is the volume. Flux means the flow per unit volume. This is the total flux to, suppose you can say this is not flux, it's mass of the fluid through the volume, mass of the fluid through the cubical volume per second. So this is portion is flux, is per unit volume per second. So it is the flux of the fluid or you can say flux of the fluid, flux of the velocity. So it is rho times, this is the flux. So this can be written as del rho v, where rho is here mass per unit volume, which is scalar quantity can taken out in this and also written like this. And if you open it, you will get the same result. So it is like this. I am writing it like this. So it is rho del dot v. So it is can be written as rho is del by del xi is del by del yj plus del by del zk, and this is the velocity. So it is vxi vyj vzk. If you operate, this will give you dx will operate on this, I dot I will be 1, I dot j will be this. So it will be dx by dx plus this will operate on this, so dy dvz by dz. So this is the same, so you can write this. So it means the divergence of any field is the flux per unit volume. This is the volume, but this is the per unit volume. So you can say that the divergence of any field is the flux of A. Flux of A means A dot ds. This is the flux divided by volume, where volume tends to 0 and limit delta V tends to. Or in another way, you can, if you write like this, you will multiply by volume here and integrate the whole volume sets dv. It will give you A dot ds. And from volume integral you are going to surface integral, and this is called Gauss's divergence theorem. So in the next class we will do gradient and then record. Okay, thanks.